The strange thing is that the question already assumes something we rarely question. We usually ask what the universe is made of: matter, energy, particles, fields. But there is a deeper assumption hiding underneath all of that. Why does any of it follow mathematical structure at all? Because the moment you write a physical law, you are doing something unusual. You are claiming that reality does not just behave consistently. It behaves in a way that can be compressed into symbols, equations, and relationships that exist in pure thought. That is not obvious. In fact, it is almost unnatural. A rock falling, a planet orbiting, light bending through space, all of it can be written as mathematics. Not approximately, not loosely, but with extreme precision. In many cases, we predict phenomena before we ever observe them, purely from equations. So the question is not just why does math describe reality? It is deeper. Why does reality allow itself to be described this way at all? To understand this, we have to be careful, because there are three possible directions this question can go. 1. Mathematics is invented by humans, just a language we built, and we are forcing patterns onto nature. 2. Mathematics is discovered, meaning it already exists independently, and we are slowly uncovering it. 3. Something more radical. Reality itself is mathematical at its core, and what we call physics is just us reading its structure. Each of these possibilities leads to a completely different picture of existence. Let's begin with the most intuitive one: mathematics as a human invention. At first glance, it feels reasonable. Numbers were created to count objects. Geometry was created to measure land. Calculus was created to describe motion. Every mathematical tool seems to have a practical origin. But this explanation starts breaking the moment we look at advanced physics. Take Einstein's general relativity. It was not designed to fit experimental data by curve fitting. It came from pure mathematical reasoning about geometry and spacetime curvature. At the time, it looked like abstract, almost unnecessary mathematics. Yet decades later, we confirmed it predicts reality with extreme accuracy. Gravitational lensing, black holes, time dilation, GPS corrections. The mathematics was more intelligent than intuition. This pattern repeats across physics. Maxwell's equations predicted electromagnetic waves before they were observed. Dirac's equation predicted antimatter before it was discovered. Pure mathematical consistency kept revealing new layers of reality. So we hit a problem. If math is just a human invention, why does invented structure consistently predict unknown aspects of the universe? This leads us to the second idea. Mathematics is discovered, not invented. In this view, mathematical structures exist independently of us. The number pi was not invented. It was always true that the ratio of a circle's circumference to its diameter is fixed in Euclidean space. We simply found it. But this raises an even deeper question. Where does this mathematical realm exist? Because mathematical truths are not physical objects. They do not sit in space or evolve in time. The equation 2 + 2 = 4 is not located anywhere in the universe, yet it seems to be universally valid. So if mathematics exists independently, it exists in some abstract realm of necessity, not physicality. But then we face a strange conclusion. If reality follows mathematics, and mathematics exists independently, then physical reality is somehow subordinate to abstract structure. This is where things start becoming uncomfortable for intuition, because it implies the universe is not fundamentally material, it is relational. Structure comes first, matter comes second. And that leads to the third possibility, which is the most extreme and also the most discussed in modern theoretical physics. Reality is mathematical. Not described by mathematics, not modeled by mathematics, but actually composed of mathematical structure. This idea is associated with approaches like mathematical universe hypotheses in theoretical physics, where the universe is not made of stuff,
but of relations that are inherently mathematical. At this point, it sounds philosophical, but it has a serious motivation. Physics keeps stripping away substance. Atoms were once thought to be solid particles. Then they became nuclei and electron clouds. Then quantum fields. Then excitations of fields. Now, in modern quantum field theory, particles are not things. They are states of underlying fields. And fields themselves are defined mathematically, not physically in the classical sense. So the deeper we go, the less thing-like reality becomes, and the more structure-like it appears. But we still haven't answered the core mystery. Even if reality is mathematical, why this mathematics? Why these equations and not others? Why does our universe select a specific, consistent structure instead of infinite possible ones? To approach that, we need to shift perspective away from humans entirely. Imagine a universe where no observers exist. No brains, no measurement, no interpretation. Just structure evolving. Would mathematics still be true there? Most physicists would say yes, because the laws would still operate consistently. This suggests something important. Mathematics might not be describing reality from the outside. It might be what consistency feels like from inside the system. In other words, what we call laws of physics might simply be the minimal set of rules that prevent logical contradiction in a self-consistent structure. But this still leaves a gap.
Why should reality be consistent at all? Why not randomness without structure? Why not contradictions? Because even randomness in physics is not truly structureless. Quantum randomness, for example, still follows probability distributions governed by precise mathematical rules, like the Schrödinger equation. So even randomness is structured. This hints at something deeper. Structure might not be optional. It might be the only way existence can exist. Now we are approaching a key turning point in this discussion. But before going further, we need to build more physical grounding. Because so far, we have been talking about mathematics in abstraction. But in physics, mathematics enters reality in a very specific way, through symmetry. Symmetry is one of the most powerful principles in modern physics. It is not just aesthetic, it is foundational. When a system has symmetry, it means certain transformations do not change its fundamental behavior. For example, rotating a perfect sphere does not change it. Shifting time forward does not change physical laws. Moving through space does not change physics. These symmetries are not decorative. They directly generate conservation laws. This is formalized in Noether's theorem, one of the deepest results in theoretical physics. Every continuous symmetry corresponds to a conservation law. Time symmetry means energy conservation. Space symmetry means momentum conservation. Rotational symmetry means angular momentum conservation. This is not philosophical. It is mathematically exact and experimentally confirmed. So here is the key insight. Physics is not just described by mathematics. Physics emerges from constraints of symmetry, and those constraints are mathematical by nature. This begins to hint that mathematics is not something we apply to reality after the fact. It is something reality cannot escape. And now we are ready to go deeper into why these symmetries exist at all, why quantum mechanics insists on probabilistic structure, and why spacetime itself behaves like a geometric object rather than a passive stage.
What we need to confront next is something subtle. Even if mathematics describes reality extremely well, that does not automatically explain why the mapping is so tight. In modern physics, the effectiveness of mathematics is not treated as magic anymore. It is increasingly treated as a consequence of something deeper, constraints on what any consistent physical theory is allowed to me. One of the strongest modern ideas is that physical laws are not chosen from arbitrary mathematical structures. Instead, they are heavily filtered by consistency conditions, such as locality, unitarity, symmetry, and computability constraints. This perspective shows up across quantum field theory, quantum gravity research, and information-based reconstructions of physics. For example, in quantum field theory, not every mathematically possible equation is physically allowed. The structure must preserve unitarity, meaning total probability is conserved, and must avoid infinities that cannot be renormalized. These are not aesthetic choices, they are hard constraints that eliminate most mathematical possibilities. So what looks like math describing reality may actually be reality being the subset of mathematical structures that survive consistency filters. This idea becomes even sharper in modern work on quantum foundations, where physicists try to reconstruct quantum mechanics from informational axioms rather than physical intuition. In approaches like reconstruction programs of quantum theory, the starting point is not particles or waves, but constraints like probabilities must be consistent under composition. Information cannot be cloned perfectly, no cloning theorem, and measurements must obey non-classical update rules. From these constraints, the full mathematical structure of quantum mechanics can be derived. This is a major shift in thinking. It suggests quantum theory is not an arbitrary mathematical model fitted to experiments, but a logical necessity once certain informational rules are imposed. A similar pattern appears in spacetime physics. General relativity is not just geometry applied to gravity. It emerges from demanding that physics be locally invariant under coordinate transformations, and that energy momentum is conserved under those transformations. In more modern language, the Einstein field equations are tightly constrained by diffeomorphism invariance and geometric consistency. So again, mathematics is not being selected freely, it is being forced.
This leads to a stronger formulation of the original question. Instead of asking why mathematics describes reality, we may need to ask, why does any consistent reality automatically generate mathematical structure? At this stage, we enter a deep result from theoretical physics philosophy, the relationship between symmetry and law. In modern physics, symmetry is not a property of laws. It is often treated as the origin of laws. A law of physics is essentially a statement that remains invariant under a set of transformations. This is not just conceptual, it is formalized through group theory, one of the most abstract branches of mathematics ever developed. And what is striking is that group theory was not invented for physics. It was developed to study abstract algebraic structures. Yet it turned out to be exactly the language required to classify particles in quantum field theory through representations of symmetry groups like SU2, SU3, and the Poincare group. This is one of the strongest empirical pillars behind the mathematical structure is unavoidable view. The fundamental particles of nature are classified not by substance, but by symmetry representations. Even the standard model of particle physics is essentially a symmetry structure. SU3 times SU2 times U1. This is not an approximation. It is the organizing backbone of all known particle interactions. At this point, something interesting happens. The distinction between physical law and mathematical structure begins to blur. Because a symmetry group is a purely mathematical object, but it also dictates what particles can exist, how they interact, and which processes are forbidden. So instead of mathematics describing physics, we find physics is what remains when only symmetry-consistent mathematical structures are allowed. Now we can go one level deeper into something more recent and less commonly discussed in popular explanations. In quantum gravity research, especially approaches influenced by holography and information theory, spacetime itself is increasingly treated as emergent. In holographic duality, often associated with string theory research, a gravitational system in a volume can be equivalent to a non-gravitational quantum system defined on its boundary. This suggests that spacetime geometry is not fundamental, but encoded in quantum entanglement patterns. In this view, geometry is not primary. Information structure is. That is a radical reversal. Space and time become secondary descriptions of deeper algebraic or informational relations.
If this is correct, then mathematics is not just describing reality, it is describing the substrate from which spacetime itself emerges. So the effectiveness of mathematics is no longer mysterious, it is expected, because what we call reality is already a mathematical structure expressed through constraints on information.
But there is still a deeper issue that even this picture does not fully resolve. Why should informational consistency rules exist at all? Why not a meta-reality where even logic breaks down? Here, we reach a limit similar to what appears in Gödel-type arguments in physics philosophy. Some modern work has explored whether a final theory of physics could be incomplete or undecidable in a formal sense, meaning no finite mathematical system can fully capture all physical truths without self-reference issues. This is not just abstract logic. It appears in discussions about whether a theory of everything could ever be final, or whether it would always generate new, undecidable extensions depending on observational context. In that sense, mathematics might not be a perfect container for reality. Instead, reality might continuously outrun formal systems, while still remaining locally describable by them. So we arrive at a more refined picture than the classical math works unreasonably well framing. Not why does math describe reality, but rather why does reality always appear as a locally compressible mathematical structure, even if globally it may not be fully compressible? This connects directly to modern views in theoretical physics, where laws are seen as effective, scale-dependent descriptions rather than absolute rules. At small scales, quantum fields dominate. At large scales, space-time curvature dominates. At intermediate scales, thermodynamics and statistical mechanics dominate. Each layer has its own mathematical structure, but none is necessarily the final layer. This suggests mathematics is not a single language imposed on reality. It is more like a hierarchy of compression schemes that remain valid within different regimes of observation. So mathematics works not because reality is made of math, but because any stable structure must generate describable regularities when viewed through limited information access. One of the most important shifts in modern theoretical physics is the movement away from laws governing matter toward constraints on information flow. This shows up in several independent research programs that surprisingly converge. In quantum information theory, the structure of quantum mechanics can be derived from operational constraints on how information behaves. In other words, instead of starting with wave functions, you start with rules like
information can't be copied perfectly. No cloning theorem, Wooter-Zurich, 1982. Measurements disturb systems irreversibly. Probabilities must compose consistently across sequential experiments. From these minimal assumptions, the full Hilbert space formalism emerges. This is already a strong hint that the mathematics of quantum theory is not arbitrary. It is the inevitable geometry of consistent information processing. Now, extend this idea further, from objects to relations, from substance to structure, from material to constraints on transformation. At this point, the question, why does mathematics describe reality, becomes less relevant than a sharper one. Why does consistency force relational structure to behave like mathematics? Now we bring in another deep idea from modern theoretical physics: effective theories and universality. One of the most powerful discoveries in physics is that many different microscopic systems converge to the same macroscopic behavior. In modern quantum gravity research, especially holographic approaches inspired by the ADS-CFT correspondence, Maldacena, 1997, spacetime geometry is not fundamental. It emerges from quantum entanglement structure in a lower dimensional theory. A key result behind this is the Ryu-Takayanagi formula, 2006, which relates geometry, area of minimal surfaces in spacetime, to entanglement entropy in a quantum field theory. This is not metaphorical. It is a precise mathematical equality. Spacetime curvature equals entanglement pattern.
So what we previously called space is increasingly understood as a bookkeeping device for correlations. This leads to a striking reinterpretation. Distance is not primitive. Geometry is not primitive. Even locality may not be primitive. What is primitive is the structure of correlations.
At this level, mathematics stops being a language applied to reality and becomes the only consistent way to encode relational structure without ambiguity. Now we go deeper. If spacetime emerges from entanglement, then the universe, at the most fundamental level, is not a collection of objects, but a network of informational constraints evolving under unitary rules. And unitary evolution itself is not arbitrary. It is the only class of transformations that preserve total probability in a complex vector space. So again, mathematics appears not as a description we choose, but as the only framework that avoids contradiction in how information evolves. This idea connects to something more abstract in mathematical physics: category theory and structural realism approaches. In these frameworks, what matters is not what objects are, but how they relate under transformations. Objects lose meaning outside their relational structure. This is important because it mirrors what quantum field theory already suggests. Particles are excitations of fields, fields are operator value distributions, and what remains invariant under transformations is what we call physical reality. So the ontology shifts from objects to relations, from substance to structure, from material to constraints on transformation. At this point, the question, why does mathematics describe reality, becomes less relevant than a sharper one. Why does consistency force relational structure to behave like mathematics? Now we bring in another deep idea from modern theoretical physics: effective theories and universality. One of the most powerful discoveries in physics is that many different microscopic systems converge to the same macroscopic behavior.
This is the principle behind renormalization group theory, Wilson, 1971. Systems with completely different underlying details can flow toward the same fixed points, producing identical large-scale laws. This is why fluids, magnets, and quantum fields can share mathematical structure, even though their microscopic constituents are different. So what looks like universal mathematical law may actually be a convergence phenomenon of many possible underlying structures towards stable fixed points of consistency. This weakens the idea that there is a single true equation of reality. Instead, there may be a landscape of possible microstructures that all reduce to similar macroscopic mathematics. Now we reach a more speculative but actively studied frontier: emergent spacetime from tensor networks. In approaches like MERA, multi-scale entanglement renormalization ansatz, spacetime geometry can be modeled as a computational network where entanglement defines connectivity. Distances arise from graph depth, not pre-existing geometry. This means geometry is literally computed from information flow. In such models, the universe is not in space. Space is a result of computation-like structure. At this level, mathematics is not just describing reality. It is the only stable compression of computational processes that remain invariant under coarse graining. Now we confront a deeper conceptual bottleneck. If everything reduces to information and consistency rules, why do those rules themselves exist in a mathematically structured form? Here, physics begins to overlap with logic and foundations of mathematics. Gödel's incompleteness theorems show that any sufficiently powerful formal system contains true statements that cannot be proven within the system. This implies that no single mathematical framework can fully capture all truths about itself. In physics interpretation discussions, this raises a radical possibility. If the universe is a formal system, it may be inherently incomplete from inside.
meaning any observer embedded in the system can only ever access partial mathematical projections of a deeper structure. This would explain why physics always progresses. Every time we find deeper laws, we discover new layers that require new mathematics. Newtonian mechanics, to special relativity, to general relativity, to quantum field theory.
Each step is not a correction, but a change in the mathematical lens required for consistency at new scales. So mathematics does not just describe reality, it tracks the limit of consistency under increasing observational resolution. Now we can connect everything so far into a single, coherent, advanced picture. What we call reality behaves like a hierarchy of stable informational structures. Each level of this hierarchy is constrained by symmetry requirements, information consistency, renormalization stability, compositional probability rules, invariance under transformation. These constraints are precisely what mathematics formalizes. So mathematics is not chosen because it is useful. It is unavoidable because any stable structure that supports observers must exhibit invariance patterns that are mathematically representable. At this stage, the deepest modern view emerging from several fields is not that math describes reality, but that reality is what remains invariant under all consistent ways of encoding information. This is why mathematics appears everywhere, not because the universe speaks math, but because math is what invariance looks like when written down. A major line of research in modern theoretical physics suggests that Einstein's field equations may not be fundamental laws, but thermodynamic equations of state. This idea originates from work by Ted Jacobson in 1995, who showed something surprising. If you assume that entropy is proportional to horizon area and that energy flow obeys the Clausius relation, delta Q equals T delta S, then Einstein's equations of general relativity can be derived as a consequence. This is not an analogy, it is a derivation, meaning gravity might not be a force in the fundamental sense, but a macroscopic statistical effect of microscopic degrees of freedom. If this is correct, then space-time curvature is like pressure or temperature, not fundamental, but emergent from underlying microstates. This shifts the role of mathematics again, because thermodynamics is already a statistical compression of microscopic behavior. So what we call geometry may actually be a large-scale mathematical summary of unknown microinformational dynamics.
Now, we connect this to entanglement-based gravity approaches. In modern holographic interpretations, space-time geometry can be reconstructed from quantum entanglement entropy. A key idea is that spatial connectivity corresponds to entanglement strength between subsystems. So if entanglement changes, geometry changes. This leads to a striking implication. Geometry is dynamic because information structure is dynamic. In this view, the Einstein tensor is not describing a fundamental field. It is encoding how entanglement is distributed. This connects to ideas like entanglement equals geometry, seen in ADS-CFT-based research programs, where spacetime in a bulk region is encoded in a boundary quantum field theory. Now we can reframe the original mystery in a sharper way. We are not asking why mathematics describes matter. We are discovering that matter, geometry, and gravity are all derived expressions of a deeper informational substrate. At this level, mathematics is not an external language. It is the natural coordinate system of informational consistency. Now we go even deeper. One of the most important structural ideas in modern physics is the principle of extremization. Many physical laws can be written as conditions that minimize or extremize some functional. Classical mechanics, action minimization. Optics, Fermat's least time principle. General relativity, Einstein-Hilbert action extremization. Quantum mechanics, path integral summation over extremal histories. This suggests that evolution itself is governed by optimization principles. In modern form, this is expressed through the action principle.
S equals integral L dt. But the deeper question is not what S is, but why reality follows extremal structure at all. One interpretation in modern theoretical physics is that extremization is the only way to maintain global consistency across all possible histories simultaneously. In the path integral formulation, Feynman, every possible trajectory contributes, but interference cancels most paths, leaving stable classical behavior as a stationary phase condition. So classical reality emerges from destructive interference of all non-consistent histories.
This is already a radical idea. Reality is not a single trajectory, but a sum over possibilities, filtered by mathematical phase consistency. Now connect this back to information theory. The phase of quantum amplitudes behaves like a computational encoding of relational constraints. Interference patterns enforce global consistency conditions that resemble logical constraints in a distributed system. So again, mathematics is not imposed. It is what survives consistency under superposition. Now we move to a more abstract frontier: spacetime as an emergent computational geometry. In tensor network models and quantum error correction interpretations of holography, spacetime is treated like a code. This is not metaphorical language. It is a structural mapping. Bulk spacetime, encoded logical information. Boundary theory, raw informational substrate. Geometry, error-correcting code structure. In these models, distances correspond to how robustly information is encoded against perturbations. So geometry becomes stability of information. This directly links to why mathematics appears so rigid. Mathematical structure is exactly what stability under transformation looks like. Now we go further into a subtle point that appears across multiple research directions. In quantum gravity and cosmology, there is a recurring idea that spacetime may not be continuous at the deepest level. Approaches like loop quantum gravity suggest discrete geometric spectra for areas and volumes. String theory suggests extended objects and dualities where geometry changes representation. But both approaches share a common feature.
Classical geometry is not fundamental. Instead, geometry is emergent from algebraic or combinatorial structures. This reinforces the idea that mathematics is not describing a pre-existing space. It is generating space as a secondary phenomenon. Now we reach a deeper conceptual shift. If space is emergent, then locality is emergent. And if locality is emergent, then causality may also be emergent. That means what we call cause and effect might be a macroscopic projection of deeper non-local informational constraints. At that point, mathematics is not describing events in time. It is describing constraints on relational consistency across a non-temporal structure. This is where some modern approaches intersect with ideas like timeless formulations of physics, where the universe is treated as a static constraint satisfaction structure rather than a dynamically evolving object. In such a framework, time is not fundamental evolution. It is a parameterization of correlations between states. Now, instead of asking why mathematics describes reality, we begin to see a stronger statement emerging from multiple independent lines of research. Mathematics appears because any structure that can support consistent observation must reduce to invariant relational constraints under compression. In simpler terms, if something can be observed repeatedly without contradiction, it must have a mathematical core. Now we are approaching a deeper layer involving quantum reference frames, relational quantum mechanics, and recent work in category-theoretic physics, where even states are replaced by morphisms, transformations, and identity is defined by behavior under composition rather than intrinsic properties. This continues to dissolve the idea of substance entirely. We are now operating in a regime where objects become processes, properties become invariants, reality becomes compositional consistency network.
For centuries, physics searched for the smallest object. First, atoms, then electrons and nuclei, then quarks, then quantum fields. But every time a supposedly fundamental object was found, a deeper layer transformed it into something more abstract. The trajectory of physics has been moving steadily away from substance and toward structure. This becomes especially apparent in relational approaches to quantum theory. In ordinary thinking, an object possesses properties independently. A particle has a position. A particle has momentum. A particle has energy. Quantum mechanics repeatedly resists this picture. In several interpretations, properties are not absolute features of isolated systems. They arise only through relationships between systems. One influential example is relational quantum mechanics, developed by physicist Carlo Rovelli. The core idea is startling. There is no observer-independent state of a system. Instead, every state description is relative to another physical system. In everyday life, this sounds strange because classical physics trained us to imagine an objective world carrying fixed properties. Quantum mechanics suggests something different. What exists fundamentally may not be objects with attributes. What exists fundamentally may be interactions. If true, then mathematics becomes unavoidable because mathematics excels at describing relationships. Numbers are relationships. Functions are relationships. Groups are relationships. Categories are relationships between relationships. The deeper physics goes, the more reality seems to resemble mathematics, because mathematics is the study of structure itself. Now another development enters the story: quantum reference frame research. Traditionally, physics assumes an external frame of reference, a coordinate system, a clock, a ruler. But recent theoretical work investigates what happens if every reference frame is itself a quantum object. Then perspective becomes dynamical. Different observers may literally assign different spacetime descriptions to the same quantum process. This is not philosophical speculation. It is a mathematical consequence of treating observers quantum mechanically.
As a result, quantities we once considered fundamental may actually depend on informational perspective. This begins to blur the distinction between physical reality and informational description. The universe starts looking less like a collection of things moving through space and more like a network of mutually consistent viewpoints. Now, something fascinating happens. When physicists study these structures, increasingly they encounter mathematics that was developed long before anyone imagined physical applications. This phenomenon has occurred repeatedly throughout history. Non-Euclidean geometry was created in the 19th century as pure mathematics. Decades later, it became the foundation of general relativity. Group theory was developed as abstract algebra. It became essential for particle physics. Differential geometry became the language of gravity. Hilbert spaces became the language of quantum mechanics. Fiber bundles became central to gauge theories. Category theory, once considered among the most abstract branches of mathematics, is now appearing in quantum foundations and quantum gravity research. The pattern is remarkable. Mathematics often seems to know physics before physicists do. This observation led Nobel Prize-winning physicist Eugene Wigner to write about what he called the unreasonable effectiveness of mathematics. But modern researchers increasingly suspect that the effectiveness may not be unreasonable at all. If physical reality is fundamentally structural, then mathematics and physics are not separate domains. They are studying the same thing from different directions. Mathematics explores all possible consistent structures. Physics identifies which structures are instantiated in our universe. Now we move toward one of the most astonishing developments in recent decades: scattering amplitudes.
Again and again, space-time loses its status as fundamental. Again and again, abstract structure survives. Now consider another mystery:
The standard model of particle physics is astonishingly successful. It predicts experimental outcomes with extraordinary precision. Some measurements agree with theory to more than 10 decimal places. Yet, the standard model contains numerous numerical parameters that must be inserted manually. Masses, coupling strengths, mixing angles. Why these values? Why not different ones? Physics currently has no accepted answer. This is important because it reveals a limit to mathematical explanation. Even if mathematics describes reality perfectly, we still need to explain why our universe selected one particular mathematical realization among countless possibilities. This question becomes even sharper in cosmology. Modern theories often generate vast landscapes of mathematically consistent universes. Different dimensions, different constants, different vacuum states, different physical laws. Some versions of string theory suggest enormous numbers of possible solutions. Estimates have reached values like 10 to the 500 possible vacuum configurations. Whether these configurations correspond to physically realizable universes remains debated. But the implication is clear. Mathematical consistency alone may not uniquely determine our universe. Something else may be required. Selection principles, anthropic constraints, dynamical mechanisms, or perhaps a deeper mathematical rule not yet discovered. And here the mystery becomes even more fascinating, because the more mathematics succeeds, the more it amplifies the question. Why this mathematics? Why these symmetries? Why these constants? Why this structure instead of another equally consistent one? The success of mathematics does not eliminate mystery. It sharpens it.
Each breakthrough reveals a deeper level where reality appears even more mathematical than previously imagined, while simultaneously exposing new questions about why that mathematical structure exists at all. And as we move further into current research on emergence, information, quantum gravity, and cosmology, the distinction between physical existence and mathematical existence becomes increasingly difficult to draw. Perhaps that is the most surprising discovery of all. For centuries, we believed mathematics was a tool created by the human mind to describe the universe. But the deeper science advances, the more that picture begins to reverse. Mathematics does not merely appear useful, it appears woven into the very fabric of reality. Every layer we uncover seems to reveal another level of structure, from planetary motion to quantum fields, from space-time geometry to entanglement networks, from conservation laws to the symmetries governing elementary particles. The universe repeatedly presents itself in a form that can be captured by mathematical relationships. And yet, the deepest mystery remains unsolved.
Why should reality possess such structure in the first place? Why should abstract entities that exist in the realm of pure logic correspond so precisely to the behavior of stars, atoms, black holes, and galaxies? Why can equations written on paper predict phenomena that have never been observed before? Why does a universe capable of producing conscious observers also happen to be a universe that can be understood through mathematics? Modern physics has provided remarkable insights, but no final answer. Some researchers believe mathematics is a language. Others believe it is a discovery. Others still suspect that reality itself may be fundamentally mathematical. Perhaps future generations will uncover a deeper principle from which both mathematics and physics emerge. Or perhaps the connection between them is not a problem waiting to be solved, but a clue pointing toward a level of reality we have not yet learned how to see. For now, we are left with a profound realization. When we look through a telescope, build a particle accelerator, measure the curvature of spacetime, or explore the quantum world, we are not merely studying matter and energy. We are encountering patterns, structures, relationships. And somehow, those relationships can be written in the language of mathematics. Whether mathematics is humanity's greatest invention, our greatest discovery, or the hidden foundation of existence itself, remains one of the deepest unanswered questions in science. And perhaps that mystery is telling us something extraordinary. The universe is not only stranger than we imagine, it may be stranger than the very mathematics we use to imagine it.